Hello everyone, I'm Michelle Yulong, from Wuhan University. Upcoming time, I am honored to share our work, Variance Weight Distribution Network-Based Noise Sample Learning for Robust Person Ray Identification. I will introduce our work from introduction to summary. Firstly, introduction. As we know, person ray identification is the person retrieval task of associating images with same identities taken from different cameras, or from the same camera and different occasions. Given a query person image, it aims to retrieve person images of the same identity from Gale Ray acquired by different cameras. Person ray identification is one of the growing communities of computer vision research, and is imperative for the intelligent video surveillance system. With increasing demand for public safety, there have been extensive studies on person ray identification in different aspects. Recently, it has attracted numerous researchers to investigate. In recent years, many deep learning-based models have been designed to solve various problems. With the help of the powerful ability of deep learning to extract features, most recent ray identification models therefore employ deep convolutional neural networks to learn a feature embedding space that is robust against the appearance changes as well as discriminative against imposters. The common procedure of a CNN model for person ray identification is directly mapping an image as a feature vector in the feature space. As the performance of state-of-the-art ray identification models on public benchmarks closes to saturation, more realistic challenges in real world are being considered. With the rapid development of person detection, instead of using manually cropped person images, recent ray identification benchmarks all provide person images produced by off-the-shelf person detectors. However, noisy data commonly exists due to false labeling, person detector errors, or occlusions in real world, as illustrated in figure. The figure is illustration of noisy samples on Market 1501 and Dukem TMC, mainly including outlying samples and label noise samples. The blue box is caused by person detector errors or occlusions, and the red box is due to human annotation errors. Each pair of images have the same identity, with the inner on the left and the outlier on the right. Both types of noisy data can influence model training, while they are ignored by most ray models. To effectively solve the two problems of noisy labels and outlying samples in person ray identification, we propose a variance weight distribution network, VWDNet. As shown in figure, there's illustrative comparison of the feature space learned by a conventional CNN ray identification model and our VWDNet in the presence of noisy samples. With VWDNet, each person image is represented by a feature distribution, instead of a feature vector as in traditional CNN. In particular, each image is represented by a Gaussian distribution T. The mean of the distribution represents the normal feature vector for ray identification matching, while the variance measures the uncertainty of the features, that is given a noisy training sample, rather than forcing it to be closer to other inliers in the same class. VWDNet computes a large variance, indicating that it is unsure what feature values should be assigned to that sample. In this paper, our contributions are as follows. Firstly, the problem of learning ray identification models that are robust to both labeled noise and outlier samples is identified for the first time, and a unified solution is given. Secondly, feature distribution learning is proposed, which treats each learned deep feature as a distribution to account for feature uncertainty, and to mitigate the effect of noisy samples. Finally, rectifying label learning is designed so that noisy labels can be rectified for training and model optimization. Secondly, enter the methodology section. This is architecture of the variance weighted distribution network, VWDNet. As shown in figure, the method contains two modules, which are Feature Distribution Learning Module and Rectifying Label Learning Module. Feature Distribution Learning Module consists of two main branches. One branch generates the mean vector, which constructs the intra-class center, and two, the other branch generates the covariance matrix. This module represents image as a feature distribution, the input is person image, and the output is predicted class To minimize the negative impact of noisy labels to the model, we introduce the Rectifying Label Learning module after the feature uncertainty distribution to rectify the noisy labels and optimize the network parameters. This module assists to predict the labels of the input imag. The input is predicted class score, and the output is predicted label. Different from the traditional baseline, feature distribution learning module represents person images as feature vectors. Our method estimates the variance of feature vectors produced by the embedding network, i.e., feature uncertainty. In other words, the outputs of our VWD-net are transformed into Gaussian distribution by the mean mu and variance delta over the original feature vector. As shown in figure, the specific implementation is such that we delete the penultimate layer and then add 2 new layers after the penultimate layer, which are calculating for the mean mu and variance delta. As shown in red box, similar to conventional baseline model, it is under cross-entropy measurement by softmax and cross-entropy loss. As shown in orange box, this branch can get the variance delta, with the purpose of avoiding the variance collapses to zero during the training process. In order to increase the uncertainty level of the overall samples, we introduce a feature uncertainty loss function to ensure a good uncertainty of the entire model training. Inspired by cross-entropy, we use entropy to measure the uncertainty of individual training samples with required variance delta. Thus, the entropy of an arbitrary Gaussian distribution can be formulated. Then the entropy for the ith image is SI. The Rectifying Label Learning module assists to predict the labels of the input images. As mentioned above, clean data with correct labels facilitates the process of training a better performing ray identification model. Therefore, the model trained with clean data can assist to predict the labels of the input images, and thereby serve to rectify the noisy labels. Hence, we propose rectifying label learning, which can take into account both labeled and predicted labels, and it is defined as follows. Then, to widely investigate the robustness of current ray identification models, we conduct extensive experiments. We use 2 commonly used large-scale person ray datasets, Market 1501 and the Ducom TMC, respectively. In this paper, we use ResNet 50 as the backbone to extract feature, in order to explore the influences of label noise on model training. We increase the percentage of label in within this experiment to show its robustness. 2 types of noise are considered, random noise and pattern noise. For each noise type, 3 percentages are considered, 10%, 20%, and 50%. In total, we divide the experimental training procedure into 2 steps. The specific experimental settings and implementation detail. We adopt rank K and mean average precision map to evaluate our method. In particular, B is ResNet 50 baseline, H is bootstrap hard, S is bootstrap soft, C is cleannet, D is distributionnet, and V is our VWD-net. We can observe the following results. 1. Our VWD-net has the best T performance in all compared methods. 2. Pattern noise has a greater impact on the performance of the model compared to random noise, which also indicates that pedestrians wearing similar clothes are more difficult to recognize. 3. 50% noise has the greatest impact on the performance of the model. But of course this is a particularly extreme simulation setting. In reality, it should be about 10% minus 20%. 4. VWD-net has a performance improvement compared to distribution-net improved, which indicates a significant correction result for our rectifying label. Finally, we make the summary. To summarize, we propose variance-weighted distribution network, VWD-net, including feature distribution learning module and rectifying label learning module. Especially, distribution learning module represents each learned deep feature as a distribution to account for feature uncertainty and to mitigate the effect of noisy samples, and rectifying label learning module optimizes the trained data by correcting the incorrect labels to improve the network performance. The effectiveness and robustness of our method is verified by extensive experiments. In the feature, we will further explore how well noise affects model performance. This is the end of our presentation. Thank you for your attention.